Welcome to lecture 2 of module 10. In this lecture, we're going to both verify that single photons exist and single photon sources of light exist. And we're going to tell you both how you create and detect photons and how we analyze and verify that single photons actually exist. In the process, you will also learn a better picture for what a photon actually is. So we start with what are called multimode single photons. Because a single frequency is only well defined for a wave that actually extends an infinitely long amount in time, there really are no photons that exist that correspond to a single mode or a single photon frequency. Instead, what we have to do is we have to describe photons in terms of linear combinations of many different modes. We call this a multimode photon, or a wave packet of a multimode photon. This is what we're going to describe how to do next. And the real photon is emitted in this wave packet, which is going to be given by the following form. So the state psi is going to be a sum over L CL times the single photon states in each mode L. CL are just numbers, they're coefficients. We're going to choose those numbers as a Lorentzian, which is a very particular type of a functional form that has a peak at a central point and then decays like 1 over the square of the frequency away from the center. So our coefficients CL are given by a normalization constant K, e to the I omega L T0, that's really chosen for convenience, and then omega L minus omega 0, so it's centered at omega 0, and we call the line width is equal to capital gamma. We have a plus I gamma over 2. Now you can think of this as the wave function of the photon, written in a basis that is given by the multi-modes or the different modes that we have that we can excite in our box that has volume V. To work out the normalization, we have to calculate a summation over L, which we want to instead write as an integral over the frequency. So an integral from minus infinity to plus infinity d omega L, dNL d omega L times the modulus squared of the CLs, which are given by k squared omega L minus omega 0 squared plus gamma squared over 4. All right, we have to work out what this derivative is, dNL d omega L. So I want to remind you that KL can be written as omega L over C times a unit vector in the direction of the 3 different n vectors. KL is given by 2 pi over L nx comma ny comma nz. And then dNL d omega L is equal to L over 2 pi C. You see that by taking that expression for the KL, multiplying it by L over 2 pi, that changes the factor omega L over C to omega L big L divided by 2 pi C. And then you can see that if I take a differential of both sides relating d omega L to dn, you can immediately see that that density of states is going to be L over 2 pi C. So plugging that in, we get 1 is equal to L over 2 pi C, this integral d omega, k squared over omega minus omega 0 squared plus gamma squared over 4. What you see here is this is a Lorentzian that is centered on omega 0, but because my integration range is going from minus infinity to plus infinity, I can just shift omega goes to omega plus omega 0, so I get rid of that shift by omega 0 in the denominator. And now I'm going to factor out a gamma squared over 4 from the denominator. That allows me to rewrite the argument of the denominator as 2 omega over gamma. I'm going to pull a 2 over gamma from that constant on the left-hand side and make it d2 omega over gamma. And now I just do a u substitution with a 2 omega over gamma. I'm going to get an integral du 1 over u squared plus 1. That's just an arctangent, and because I'm going from minus infinity to plus infinity, it's over a period of the tangent. So that's going to equal pi, and that's going to cancel the pi that's in the denominator. And then when I solve for k, I'm going to get that k is equal to gamma c over L square root. So we find that k is the square root of c gamma over L. So I can plug that in now into the integral. Now we're going to assume that the photon is emitted at a time t0 and that it has to travel a distance z from the place where it originates to get to the detector. So we're going to use our single photon amplitude W1 of z and t, or single photon probability W1 of z and t, is equal to our efficiency S times the modulus squared of E plus of zt acting on our initial state psi of t0. So we plug in what E plus of zt is. Remember, that's the term that has the ALs in it. I get a sum over L, I epsilon L polarization, epsilon L of 1, the single photon amplitude, AL lowering operator, e to the I k sub LZ minus I omega LT, all acting on that initial state psi of t0, which is this linear combination with this Lorentzian profile that we were just describing. Now we plug in what that Lorentzian profile is. We've determined that the k is c gamma over L. So it's just a substitution, and we have this extra term that represents what that psi of t0 is. And now we look carefully at our operators. You see I have an AL multiplying an AL prime dagger acting on the vacuum. That term is non-zero only if L is equal to L prime. And if L is equal to L prime, I can replace it by its commutator, which is equal to 1. So by setting L prime equal to L, I can get rid of both the AL and the AL prime dagger. So we go ahead and do that. We now have a single summation. I'm now going to combine all those exponentials into a single term and put it into the numerator. And then I'm going to take out that I epsilon L squared, and I'm going to replace that epsilon L of 1 by its constant values. It's going to give me S times some h bar omega 0, because we're assuming the spread is relatively small, so we're approximating all of those quantum single photon amplitudes by the same frequency omega 0, and we have that 2 epsilon naught v in the denominator. We now have to evaluate that summation, which we convert into an integral. We have to put in that density of states factor L over 2 pi c. And this is an expression that isn't all that simple to integrate. It's not something that integral can just immediately be done, but it turns out we can do that integral by using contour integration. So we're going to have a little interlude and show how we can evaluate this integral using contour integration. Remember, we did study contour integration in Physics 155, and we're going to have to do an integration by residues in order to get this integral. Let's start thinking about the case where t minus t0 plus z over c is less than or equal to 0. In that case, we want to close this contour in the upper half plane. Remember, when we're trying to calculate integrals by residues, we need to be able to evaluate what the integral is over this large semicircle that we're adding to our integral. And if we can add an integral where that integral over the large semicircle is equal to 0, it's just our add 0 trick. But once we have it as a closed integral, then the residue theorem tells us that that integral is equal to the sum of the residues at the poles that are inside the contour, multiplied by 2 pi I and by the winding number of the contour as we go around the contour. Now, in this particular case, closing in the upper half plane, take a look at that exponential factor. If t minus t0 plus z over c is negative, then that factor is the exponential of I times a positive number. If I take my omega and I replace it by a complex number that's in the upper half plane, then it's going to be equal to a real number plus I times a positive number. And when I take I times a positive number and multiply it by I times a positive number, I get minus a positive number, or minus a negative number. So that function is going to behave like a decaying exponential. And as a gets very, very large, it's going to decay to 0. And then I really will be just adding 0. So that's why we close the contour in the upper half plane when we have t minus t0 plus z over c is less than or equal to 0. And of course, there are no poles inside there, because the pole is appearing when omega is equal to omega 0 minus I gamma over 2, and gamma is a positive number. Now, when we let t minus t0 plus z over c be larger than 0, then we have to close in the lower half plane, because the exponential term is going to then be decaying in the lower half plane. And here we have that one pole. That little dot inside the contour is the location of the pole. So we have to evaluate it at the pole. So when we calculate by residues, we're going to get a 2 pi I times the winding number. The winding number is -1 because we're going in a clockwise direction rather than a counterclockwise direction. There's a theta of t minus t0 plus z over c because this, remember, that's the unit step function, because this integral was equal to 0 when t minus t0 plus z over c was less than 0. And now for t minus t0 plus z over c bigger than 0, we're calculating what it is. Then I have to calculate the residue, and to calculate that, I'm going to get the integrand without the denominator in it. So I'm going to get L over 2 pi c, square root of c gamma over L, and then I have to evaluate that exponential at the point where omega is equal to omega minus I gamma over 2. So I'll get a e to the minus I omega 0, t minus t0 plus z over c, and then when I add in that plus I, or minus I gamma over 2 multiplied by minus I, I'm going to get minus gamma over 2 times t minus t0 plus z over c. So that now has evaluated that integral for us. We're able to now go back to the formula that we've been working out and plug that into the formula. We now can evaluate this integral. And using the fact that the square of a theta function is just a theta function because it's a unit step function, that e to the minus gamma over 2 becomes e to the minus gamma squared. The complex phase, the e to the I omega 0 t minus t0 plus z over c, that modulus squares to 1. I have to take a square of those different constants in front. They end up giving me L big gamma over c when all the dust settles by putting all those together. So this is the result that we get. Now let's take a look at what that looks like. So I have written for you schematically here as an example of what this experiment is going to look like. In the focus of that parabolic reflector, that's where we have our atomic sources that we're going to be exciting and that are going to do this heralded photon emission. The emitted photon is going to go along this cylindrical waveguide, and it's got to travel a distance z before it gets to the detector D. So we initialize our state when we've heralded that photon. That's when we start our clock at t0. And then we keep it open for a window. So we first make sure that our window is at least as long a time as it takes a photon to travel that distance z. And then we keep it open just a little bit longer than that. It's typically open for a range of some number of nanoseconds. And we do our measurement and see how many photons can we detect after we have heralded the photon. And this is what the experimental data looks like. So this experiment has actually been done. And what you can see here is we have this large range where the photon count is essentially 0. It's not exactly 0. You can see it's flat. That's our dark count. The dark count is random, but if I average it over a period of time, it should give us a flat background because it's the same in every time interval. And then you can see I have this very sharp rise and then this kind of exponential-like decay on the other side of the sharp rise. And the width of that tells us how big the gamma is. And it's actually a measure of the inverse of the gamma. It turns out for this particular system, it's about 4.7 nanoseconds. Each dot corresponds to a bin that has a width of about 0.4 nanoseconds. And you can see by the time I get a couple of inverse gammas, like maybe, let's say, 15 to 20 nanoseconds, by that point in time, the photon has been detected. It has a very high probability to be detected within a few inverse gammas of the onset time, which is given by the time it took the photon to travel the distance z between where the source is and where I reach the detector. All right, so that's pretty cool. We've calculated this functional form. We've actually measured it, and we find that it agrees with the functional form that we calculated. This is one way to visualize what a single photon is. A single photon is something that, after it is created, I can measure it, and I have a very high probability of measuring it within a very short time window. And once I have measured it, I can't measure it again. That's in essence what the definition of a photon is. I want to just cover a little bit more detail exactly how this experiment works. We're using this calcium cascade single photon light source. The way that that works involves shining two different lasers on the system, a chromium ion laser and a dye laser. They have to be high intensity because we're actually going to be combining and doing a two-photon process that raises us from the G level to the U level. We then just sit and wait, and there's a spontaneous emission that emits a photon, h bar omega h, down to the E level, and then the E level is only stable for a few nanoseconds or less, and then it emits an h bar omega 0. What we do is we detect the heralded photon that has a frequency h bar omega h, and that then tells us that we're going to be seeing a photon with frequency h bar omega 0 coming out within the next nanosecond or so. So we keep this open for a particular time window, and then what we do is we measure and we see what the photon is. Now, if you like to think about this in sort of the Feynman path integral type approach that we're using in modules 3 and 4 of the class, then what you can think of is it's a particle, but there's a window of time at which that spontaneous decay occurs, and that's what's giving me the width of the curve that is being measured. And then once the photon is emitted, it travels at the speed of light to the detector. So it always takes the distance z divided by c to get there from the point in time in which it's emitted. If we want to think about it in this sort of quantum mechanical way, what we can say is that the photon is put into an indeterminate state that is given by the wave packet, and that wave packet has a certain width to it. And then what I measure when I measure it as a function of time is the width that I get from the wave function, which is giving me this probability distribution for the photon. And then that's a way that you can think of it as well. They're both valid ways of thinking about what a photon is and what it means to create a curve that looks like this curve that has been measured to verify that we have a single photon source. Okay? But there's a little bit more that we have to go into in really verifying that we have a single photon source, because it turns out in this experiment, when we take light and shine it on a beam splitter, we can actually see in some cases that we measure two photons. And we're going to explain to you exactly how that works, but we have to really go through this analysis of what happens when we shine a single photon source onto a beam splitter. So we're going to have a little tutorial on beam splitters. We did cover these in Module 4, but we want to now cover it with our more advanced mathematics than what we were using in Module 4, although everything we did in Module 4 is completely valid. You don't have to unlearn any of this. This is additional material that will help you understand it in a richer way. So our beam splitter has two input ports. They're marked 1 and 2. We're only going to be sending light in on the input port number 1. Now, when that light comes into the beam splitter and the dark line corresponds to where the silvered mirror is, it can either reflect downward or be transmitted forward. But if we think of it as coming in the 2 ports, then we can actually calculate what the electric fields are, how they are related. So you think of the electric field as essentially being the arrow that we were using in modules 3 and 4. So when I come in from port 1, if I'm reflected, I'm going to reflect to port 3. So we're going to multiply that by the amplitude for reflection. That would be the number that we were using before that was equal to 0.96. But here, because it's a beam splitter, it'll be 1 over the square root of 2. And then it has a probability of being transmitted if it comes in from the 2 port. So we're going to have to add to that the transmission multiplied by the electric field that it had coming into the number 2 port. And then when it goes out in the number 4 port, if it's coming from the one direction, it is transmitted, so that gets multiplied by that T amplitude. If it is coming from the number 2 port, it is reflected, but notice it's reflected by going through glass. And when we're reflected from inside glass, we have to add 6 hours to our amplitude. That's the same as multiplying the number by -1, so that it becomes minus R times E2. So these rules that you see that I'm writing down here are just the rules we were using in Module 4 in working with the arrows. Now, the probability for detection in ports 3 and 4 are given by this single photon detection. So the rate of detecting the probability, dp3 per unit time dt, is given by this efficiency S times the modulus squared of E3 plus of R3T3 multiplied by the input photon state psi in modulus squared. And similarly in the fourth port, it's the same thing, but I'm going to use E4 of plus. And to get E3 and E4, I use that formula above and express it in terms of the input amplitudes E1 and E2, which is what I know from what my input photon state is. And if it is a single photon, I should not get any double counts within the measurement window, which will be a few nanoseconds that I'll be doing the measurement. Now, of course, not every heralded photon is actually able to be detected. So let's say that the probability to detect a heralded single photon is modulus gamma squared. What this means is if a heralded photon is emitted, for me to detect the heralded photon, to know that that next photon is coming, the probability that I'm going to be able to do that is modulus gamma squared. Then our input state is gamma times the 1 state plus the square root of 1 minus amplitude of gamma squared times the 0 state, tensor product with a 0 state in port 2 because we're not bringing any photons in on port 2. We can now use this to calculate the probability rate in channel 3. We just plug in that calculation that we did before. We have this quantum efficiency eta 3. We have that extra probability gamma squared. We then are going to get the square of the reflection amplitude, little r modulus squared. We get this theta function, and we get this e to the minus gamma T3 minus T0 minus Z3 over C. We get a similar formula in the fourth channel, with just the 3's being replaced by 4's, and the r squared being replaced by a t squared, and the efficiency being replaced by from eta 3 to eta 4. Now what we're going to do is we're going to integrate that over a few inverse gammas, and then what we're going to get is that the number that we would detect over that time integration window, that's going to be our measurement window, is going to be that quantum efficiency eta 3 times that gamma squared times r squared in port 3, and it's going to be the same thing with the eta 4 times gamma squared times t squared in port 4. The coincidents are, of course, going to be 0 for working with a single photon state. In a real experiment, we're going to actually see coincidences due to a dark background photocurrent and also due to multiple spontaneous emissions that occur within that same measurement window. We need to keep our atomic source dilute enough that we don't get a lot of spontaneous emissions in the same measurement window, but we need to have it be dense enough that we get enough that we can actually run our experiment and do our detection. So there's a delicate balance that we have to run there. We're going to let NH be the number of heralded photons. That's the number of those first photons that we detected. And then the probability for detection in port 3 is just the number I measured in port 3 divided by NH. The probability for detection in port 4 is just the number I measured in 4 divided by the number of heralded photons. And then similarly for the number of coincidences. We're going to define a parameter alpha, which is the probability for coincidences divided by P3 times P4. And if I write that out in terms of these numbers that are measured in a given interval, it's going to be NC, number of coincidences, times NH, the number heralded, divided by N3 times N4, which is the numbers measured in ports 3 and 4, respectively. Now, it turns out that single photon sources will have alpha less than 1, and classical photon sources must have alpha greater than 0. It turns out the requirement for alpha greater than 0 comes from the fact that the 2-photon detection probability is greater than or equal to the square of the single photon detection probability when I have a classical light source. And we're going to go over that in just a little bit to verify that for you. But for the moment, just assume that that's true. That then tells me that those coincidences are given by the product of P3 times P4 times NH. And then you see that I'm going to get alpha equals 1 when I plug into that formula below. So we're going to ignore the dark counts for the moment and assume that we have new extra spontaneous photoemission events occurring during a detection time interval. That fraction nu had better be less than 1, otherwise it's not going to be a very good experiment. So maybe it's on the order of 10%, 20%, something like that. And we're going to define efficiencies epsilon 3 and 4 such that we can write P3 as epsilon 3 times 1 plus nu and P4 times epsilon 4 times 1 plus nu. And the way you should think about that is I'm counting in port 3 or in port 4 according to how many photons were present. But if I actually had 2 photons spontaneously emit within that time window, then they'll have the same probability of branching into port 3 or port 4, and I just have to add them in, and they add according to the rate in which I have multiple photons appearing within a given measurement window, which is given by nu. Now, for coincidences, we're of course going to get the product of those, and you would think that I should multiply that by the product of 1 plus nu squared. But it's the product of 1 plus nu squared minus 1. And the minus 1 comes about from the fact that if it really is a single photon source and I really have only 1 photon there, then I get no coincidences because once I've measured the photon, it is gone. So PC, according to this simple model, will be 1 plus 2 nu plus nu squared minus 1, and that just becomes 2 nu plus nu squared. So alpha is then written as 2 nu plus nu squared over 1 plus nu quantity squared. And now if I separate out and I essentially do a add 0, I add 1 plus nu squared over 1 plus nu squared, and I subtract 1 plus nu squared over 1 plus nu squared, you see I'm going to get 1 minus 1 over 1 plus nu quantity squared. That term that is being subtracted is a positive number, so alpha is less than or equal to 1. And this is the reason why we say when we have a single photon light source, alpha will be less than or equal to 1. Now, this measurement has actually been done, and what we find is that with a good single photon source, we find that we get alpha less than 1. In fact, when they really turn the density down in that atomic source, so they're getting on the order of about 10% of the 10% extra double spontaneous emissions during a measurement time window, they found alpha was approximately 0.18. Of course, alpha would equal exactly 0 if I had a perfect source. All right, so let me summarize this. This is really telling you what a photon is. We have seen that the single photon state is given by this wave packet expressed in terms of these coefficients CL, where they're normalized. 1 is equal to the sum over LCL squared. This is a total number eigenstate. If I operate the total number operator on this state, I will get 1. That's because the sum over L modulus CL squared is equal to 1. But it is not necessarily an eigenstate of H, because those states have different energies for each. It's approximately an eigenstate of H, but it is not exactly an eigenstate of H. So a single photon state is an eigenstate of the total number operator, but it is not an eigenstate of the Hamiltonian. So it is not a definite energy eigenstate. It is only a definite particle number eigenstate. And the particle number eigenstate, when the particle number is equal to 1, we call that a single photon state. Now, when we measure it, it can only be observed once. Once we measure it, we destroy it. We can't see it again. It's gone. It has an extent in time that lasts only a few inverse gammas with high probability. So once I've waited a few inverse gammas, I'm pretty much going to detect it if it's present. The single photon sources of light are not just dim light, and that's a really important thing that you need to know, because dim light does not satisfy these properties that we've just expressed above, and we're going to go into that in detail in just a moment. It used to be assumed that dim light was a single photon source because the reasoning went as follows. We said, suppose my apparatus size is, say, a meter, And suppose I set it up so that on average I have only a photon going through my device, say, every microsecond. Well, a photon travels a meter in about 3 nanoseconds. So I have a spacing between my photons that's about 300 meters, and my apparatus is only a meter long. Surely I have only one photon at a time in my apparatus. But that's not true. The Hong-Ou-Mandel effect tells us photons like to bunch up, and there actually is a non-zero probability to have 2 photons in that apparatus at the same time. It's a smaller probability, but there's even a non-zero probability to have 3 photons in that apparatus at the same time. In fact, there's a finite probability to have an arbitrary number of photons in that apparatus at the same time. Now, that means that a single photon source of light is different from classical sources of light. Well, what are classical sources of light? They are described by coherent states of light. And let me just summarize for you what a coherent state of light means. A coherent state of light is an eigenstate of the lowering operator. So when AL acts on a coherent state of light alpha L, it'll give back alpha L times the state alpha L. And that state alpha L is given by the displacement operator acting on the vacuum state. And just to remind you, the displacement operator is e to the alpha L AL dagger minus alpha L star AL acting on the vacuum state. For a semi-classical state or a coherent state, what we're going to find very easily is that the single photon probability, the efficiency S times the modulus squared of E plus, that's going to equal S times that single photon amplitude epsilon L of 1 modulus squared times alpha L squared. Because remember, I have to take the expectation value of AL. But AL acting on the state alpha L just gives alpha L. And I'm taking the modulus squared of that. So I get modulus alpha L squared. Now let's look at the 2-particle amplitude. That's given by S squared E plus of RT and E plus of R prime T prime. Now each E plus has an AL in it. And I have 2 of them. But each AL, alpha L is an eigenstate of AL. So each AL gives me an alpha L. So I'll get alpha L squared. And when I take the modulus squared of that, I get modulus of alpha L raised to the 4th power. And you see, W2 is just equal to the square of W1. That's what is meant by a classical state of light or a semi-classical state of light. It's going to have that parameter alpha equal to 1. And that's the result of a classical field. So they're never single photon states. What we find is dim light will always have a small probability to have 2 photons in the measurement window during a given experiment, no matter how dim it is. And what is classical light or semi-classical light? It is incandescent light. It is light-emitting diodes. It is lasers. They're all classical light. A lot of people think that lasers must be quantum light, but no, lasers are classical light. Single photon sources are much more difficult to get than just lasers, and single photon light sources are the true quantum light. Now, this experiment of shining dim classical light on a beam splitter has actually been done, and it's actually been verified that the probability of getting those 2 photons within that measurement window is exactly what we predicted here. So it's pretty neat that you can really verify that these classical light sources actually behave classically, and they are not single photon light sources. Okay, that brings us to the end of lecture 2 of Module 10.